For the left endpoint, we would need to be a little bit careful here because x sub I is no longer a plus I delta x. The interval we're interested in is 0 to 4, and we divide the interval into n sub-interval. So the width is delta x equals b minus a over n, which is still 4 over n. The endpoints are, using the left endpoints, they are 0, and then we add delta x to this, but delta x is 4 over n, so 0 plus 4 over n is 4 over n. And then the next endpoint is 2 times 4 over n, which is 8 over n. And the next endpoint is 3 times delta x, which is 12 over n. And so the endpoints are x sub 0 equals 0, x sub 1 equals 4 over n, x sub 2 equals 2 times 4 over n, and so on. The last endpoint that we will need to use is actually x sub n minus 1, not x sub n, because we're using the left endpoint. But x sub n minus 1 is not 4. X sub n minus 1 is n minus 1 times 4 over n. Recall that if we want to have x sub 1, we would take 1 times delta x. X sub 2 is 2 times delta x. Therefore, x sub n minus 1 is n minus 1 times 4 over n, 4 over n being delta x. From this pattern, we can see that x sub I is I minus 1 times delta x. This is I minus 1 times 4 over n. And so it is not quite what we had before. Before using the right endpoint, we have x sub I equals a plus I delta x, but we can think of it that we shift it to the left, so that now if we use the left endpoint, then x sub I is a plus I minus 1 times delta x, a being 0 in this case, and again delta x is 4 over n. But regardless, we would need to use x sub I equals I minus 1 times 4 over n to set up the Riemann sum. The Riemann sum using the left endpoints is L sub n equals the sum at I go from 1 to n of f of x sub I times delta x. But remember that f of x equals x, so this is the sum at I go from 1 to n of x sub I, because again, f of x equals x, and delta x in this case is still 4 over n. Substitute the expression for xi and delta x. We have the sum as I go from 1 to n, where x sub I is 4 over n times I minus 1, or I minus 1 times 4 over n. But this is only x sub I, and x sub I is f of x sub I, where f of x equals x. We still need to multiply delta x, but delta x is 4 over n. Simplifying this, we have the sum as I go from 1 to n of 16 over n squared times I minus 1. We then evaluate this sum. The 16 over n squared doesn't depend on I, so we can bring the 16 over n squared in front of the sum. We end up with the sum as I go from 1 to n of I minus 1. To evaluate this, we would need to split the sum into 2, so we will keep 16 over n squared for now, and we only split I go from 1 to n of I minus 1 into 2 sums. After we obtain the result, we can multiply 16 over n squared after. The first sum is I go from 1 to n of I, and the second sum, being subtracted from the first sum, is still I go from 1 to n, but the argument inside is 1. We know that the sum of the first n integers, which is I go from 1 to n of I, is n times n plus 1 over 2. And the sum of 1 being added n times is n times 1, or simply n. And so the sum as I go from 1 to n of 16 over n squared of I minus 1 is 16 over n squared. And inside the sum, we obtain n times n plus 1 over 2 minus n. Before we evaluate the limits of L sub n, we should simplify this expression. This is 16 over n squared times n squared plus n over 2 minus n. The common denominator inside the bracket is 2, so we have n squared plus n minus 2n over 2. This is now 8 over n squared times n squared minus n. We can then factor out n inside the bracket to get n times n minus 1. And the n and one factor of n in the denominator canceled out, so we would end up with 8 times n minus 1 over n. And this is the left sum L sub n. As n goes to infinity, the limits of L sub n is the limits of 8 times n minus 1 over n. We can bring out the 8 in front of the limit. The limit at n go to infinity of n minus 1 over n is 1. So we see that the answer is 8.